characteristic of k not equal to 2. Theta was an automorphism of G, and theta was defined over k, so let's do it like this. And where gk are going to be the fixed, the k rational points. H is the fixed point group of theta. And we also had to map tau from G to G, where tau of G was G theta G inverse, and the image of tau I called Q, which was our symmetric space over an algebraically closed field. I defined QK, and this is really a bad notation, let me say that, and emphasize that for those of you who didn't pick this up. So this is tau of GK. This is not equal to the k rational points of Q. Yeah, so notation is really bad. So I don't have, this is totally different. And so, yeah, I didn't invent the notation, so I'm just, using it. But this is really something what's bad. This is not the k rational points of Q. Also, the name symmetric k variety is not totally appropriate. It would be better to call it the generalized symmetric space. What I'm trying to advocate is because, that's more appropriate, because it is not the variety defined over k. Okay, so we are having a P, a minimal parabola k subgroup. And we are interested in the p orbits on, and so we have that qk is isomorphic to gk mod hk. And we are interested in the pk orbits on q, or on, again, we can do this in 3 ways, that we can either have it as pk orbits on q, we can have it as hk orbit on gk mod pk, etc. in the same 3 ways. And the results are surprisingly similar. So what are the ingredients? If we have a parabola k subgroup, you're no longer looking at maximal tori, you're looking at maximal k-split tori. Yeah? And so what you do is you take A contained in P, a maximal k-split torus. And the first thing you proved of the algebraically closed field is that there was a theta stable maximal torus. So same result here. Lemma, there exists a theta stable minimal maximal k-split torus in P, and all of these, and these are conjugate under hk intersection pk. So very similar result, so this is very encouraging. So we know that all maximal k-split tori are conjugate, so we can always start this. So we can again consider the pairs PA. And so I'm going to call CK is the pairs of PA for which A contained in P is a maximal theta stable maximal torus. And yeah, my my P is always going to be, so I should probably say that P is then a minimal parabolic K subgroup. Same thing as before, but now, yeah, something I didn't mention before, but I'll get to that later. But there is natural well groups and root systems involved with all of these, and I'll get that a little later on. But we can consider the set of HK conjugation classes of maximal of theta stable maximal tori. Then Borel and Teach showed that if you fix one of these tori, then essentially all the parabolic subgroups containing that maximal theta split torus are just parameterized by the well group of the maximal K-split torus. So what we get here is that if the CK orbits under HK are going to be isomorphic, a union of I and I of the WGK of AI modulo the WHK of AI, where again we have that the set of AI are representatives of the HK conjugation classes. So, very similar result. If you remember that last time I looked at the action of arbitrary parabolic subgroups, and then I had the Borel here in the middle. For minimal parabolic K subgroups, you don't need to do that. That Borel can be just absorbed in all the rest of the information. And in general, you can often drop the Borel as long as you have a root system structure on your torus, which needs to be the center or an open, a dense subset of your, a regular subset of your minimal parabolic subgroup. So, very similar result. And I also need to get into the more technical one because that's the one I will need more often today. So let me now look at the pk times HK orbits. For this one, I'm going to a fixed theta stable maximal K-split torus. And then I define similar, but now I put the subscript K under it, is the set of x in GK for which tau of x is going to be in the normalizer in GK of A. So I basically replace maximal torus by maximal K-split torus and define the same type of objects and restrict myself to the K points. But now it is really the centralizer in G of A acts on this. And also because that will give us the same well group element and also the fixed point group of the K. So we have that Z, the centralizer in GK of A times HK acts on our script VK in the usual way. So we have that if you have an XZ acting on Y, that is X, Y, Z inverse, where X is in the centralizer in GK of A, Z is in HK, and Y is in script VK. So I could probably scribble this underneath here. So Vk is the set of the centralizer in Gk times Hk orbits on Vk. So then we get the similar theorem. You can also look at the twisted action of P onto Q. I'm not going to go through in the details because I'm not using that for today. But essentially, that theorem of S.P. Wang and myself, we never met, but we had the same results. So we got these results independently. And so P minimal parabolic K subgroup. Then we have that the pk orbits on Gk mod Hk are isomorphic to the one I already put on the board. And that is isomorphic to Ck orbits on Hk, and that is isomorphic to our set Vk. And we have similar other characterizations. So this looks very similar. The proof is totally different than you can imagine from the algebraically closed case, because the big abstraction here is that there is, so the problem is that doesn't exist in theta stable minimal parabolic K subgroup. And in general, that's not going to happen. So what you need to do is you need to conjugate these parabolic subgroups away outside of the K points where you can find something that's theta stable, and then show that you can come back again and leave the K structures fixed. So it is technically a little bit of a swamp, but yeah, the final result is nice. I should give credit to some people. If K is the real numbers, similar characterizations were obtained by Rossmann and Matsuki. More detailed by Matsuki, but Rossmann had the first characterization. And that has been used in real representation theory, as you probably know. And algebraically closed case was Springer. But then for the rest, all the other cases were open. In both these cases, you have a finite number of orbits. Now, of course, you also get finite number of orbits if K is finite. Then you get finite number of orbits. That's kind of trivial. But more importantly, that if K is local field, then finite and so that's very useful for representation theory. This breaks down almost immediately if you leave a local field. And so let me give you an example of that. And that's very unfortunate. There's nothing like a Hasse principle. You have it for all the periodics, and then it works for the rationals. Nothing like that. So G is SL2 over the rationals. let's take for our involution the most generic one we can think of, transpose inverse. B is the upper triangular matrices. Our maximal A is just going to be the diagonal. And in this case, our set VQ, and that is just straightforward calculation, is the set in GK for which, so that's the definition that tau of G is in the normalizer in GK of A. And then you find out that if G is A, B, C, D, then tau of G is B squared plus D squared minus AB minus CD minus AB minus CD, and A squared plus C squared. That is going to be in the normalizer in GK of A, if and only if AB plus CD is equal to 0. And so that means that tau of, sorry, this is script. Tau of script VQ is contained in AQ. And if you go through the calculation, then when two orbits are isomorphic, what you get then is that VQ is going to be isomorphic to all the primes. P is congruent 1 mod 4 of Z modulo 2Z. And in order to get there, you what you do, it is what you do is just take an R00, R inverse, and if you take a Z in our Borel subgroup, which Z is going to be yeah, VU 0 V inverse, and this is our tau of G. Then, if you let the Z act on this by the theta-twisted conjugation, you get that Z inverse tau G sigma G is going to be an AQ if and only if U is equal to 0. And that is just something what you need to write out. I'm sorry, this is theta. So this is really too bad for, but at least of the periodics we can do something. Don't write here. Is that still valid? Okay. How far is here? At all?
Can you just alternate the boards?
Okay. So I recently also got a description of action of general parabolic subgroup. I will very briefly touch on that, but I'm not going to go into the details because this was ugly, that one is way more ugly. So if P is just a parabolic K subgroup, and then the pk orbits on gk mod hk, so I should probably write theorem here. You can essentially identify this with the hk conjugation classes of triples P, a union of an I in J, or maybe I should take J and J of the PI and AI, where again PI is contained in P is a minimal parabolic K subgroup. But yeah, you can see that I have a union here. There is no longer a unique open orbit. And so what you look at is we have that P, H times P is going to be open. Sorry, H times Pi is going to be open in P. And I can look at that over the algebraically closed field. And there is a unique open orbit, and that breaks up a lot of K orbits. And so this is the breaking up in K orbits of the unique open orbit. And so, and then, okay, and the same is that AI is contained in PI maximal K split, and of course theta stable. So similar to the algebraically closed case, but this is this part can be a mess. And so I'm really only touching on what's happening here. For representation theory, you are really interested also in the geometry of this orbit decomposition. What are the closed orbits? What are the open orbits? Of course, you can only talk about that if you have a geometry coming from your fields. Yeah, for finite fields, there's not much of a topology there. But, and there is also, and that is really related to a natural root system corresponding to this symmetric spaces. And so I'll try to indicate how, what open orbits are, how you can get the closed orbits, how you can look at orbit closures, and also which parabolic subgroups contribute to the Planck-Gérot formula, because a lot of parabolic subgroups really don't contribute anything, and you like to single out those which gives you yeah, a nice contribution. So, so root systems of symmetric spaces. And I'll start with the algebraically closed case, and then so a torus, let me call it S, contained in G. A torus is theta split if theta of S is S inverse for all S in S. And this is a theorem by Wüst and Richardson. That if S is a maximal theta split torus, then phi of S is a root system with well group. the normalizer modulo the centralizer. You can always look at this, but it is not always a root system. And this is the natural root system of a symmetric variety or an algebraically closed case. Now we need to mix this up with maximal k-split tori. And so if you take the combination, so then S contained in G is called theta k-split. If it is theta split and k-split. Same result as maximal theta k-split. Then phi of S root system, etc., with the same well group, and the normalizer in GK of S modulo the centralizer in GK of S is the root system, well group of the root system. So very similar. So now we have the following situation. We have a maximal theta k-split torus, which we can extend on the one hand to a maximal k-split torus. And so those root systems are related to that. And on the other hand, yeah, this is not a maximal theta split torus. You can also extend it to a maximal theta split torus. And yeah, it would be nice if you can put all of that in one maximal torus. And you can. So what you can do is you start out with, so this is basically the case structure. You start out with your S here. Then you extend this year to a maximal k-split. And you extend it here to a maximal theta split. And then all of this is contained in one T maximal torus. So theorem, there exists a maximal torus T containing S such that yeah, T theta minus, and I will give you the notation for that, is maximal theta split. And T contains a maximal k-split torus. And the proof of this is basically you take the centralizer of this and you prove that it splits out in different irreducible components, which are either going to be totally anisotropic or totally, and if there is something k-split, then the involution is going to be trivial. And so, why is this nice? Now, for example, all the root systems involved here are basically projections down to the various components of the root system of the maximal torus, and the same with the well groups. So there is integrate relations of you have the well group and root system of T projecting down to these different components. So what do you think the open orbits are? usually you get something open if you get something closed if you think about it, if you fix as much as possible inside the fixed point group of the involution, because then you get the lower dimensional orbits. You get something open if you have as little as possible in common with your fixed point group, because then you have the biggest possible dimension. So basically, if you have a torus or minimal parabolic subgroup which comes from a regular element over here, it is going to be open. So so lambda in S so this is just my set of one parameter subgroups. And if I take lambda in chi of S, then x of S, then if lambda is regular, then the parabolic subgroup P lambda, which is basically consisting out of all the roots which have a positive, with lambda comma alpha is bigger or equal to 0, this is then going to be a minimal parabolic K subgroup. Sorry, that is not a minimal, it's a parabolic K subgroup. Sorry, which is not minimal. Which is minimally theta split, and I should have defined that. And theta split means that P intersection theta P is a common Levi subgroup. And so if P is a parabolic subgroup, theta P is also going to be a parabolic. And so if the involution flips as much as possible, it flips the whole unipotent radical, then it is kind of the natural opposite. So this is kind of the opposite. So we can also say this is the opposite parabolic. And this one is going to be minimal theta split. Now these parabolics give you basically give you open orbits. And they also give you the most continuous part of the Planck-Cherov decomposition. And if you take other elements which are not regular, then you are going to get other theta split tori. So if lambda is not regular, then you get other. Then you're going to get other. Then you get P is just going to be a theta split. But because that is from the fact that lambda is chosen in S, but you are going to just get the other parabolic subgroups. And these are the parabolics that contribute to the Planck-Cherov decomposition. You don't need to consider any others. And so that's very nice. This is in a paper of my brother of mine from a number of years ago. Yeah, I know that this is usually something that's a little bit hairy, so let me try to give you the SL2 example for this, where I can really work it out in details. Do I forget something? So we take here I use different notation. So T is it is a maximal torus. Is the diagonal matrices as before. U is the unipotent radical. Sorry, it is not going to be the unipotent radical. It is going to be the set of G in. It's not G. It is Q in K star modulo K star square, for which x1 square minus m inverse x2 square is equal to Q inverse as the solution. And here my involution theta is conjugation by 0, 1, m0, where m is a representative of K star modulo K star square. What we saw a couple of days ago, that all involutions of SL2 are like that. And so it basically comes down on solving this type of equation. I like to note that in general, HK is going to be Ki anisotropic if and only if m is not equal to 1. If m is 1, then H is a maximal K-split torus. So if you take this remark, then what we get is that if you start out with T I theta K-split torus, then the Well group in HK of Ti is equal to 2 if m is equal to 1. I know this is bad notation. This is modulo a square all the time, so I should probably say 1 bar, but yeah, I'm being a little bit. And minus 1 is in K star square. WHK of Ti is equal to 2 if m is in minus, so m is basically minus 1, and minus 1 is not a square, and WHK of Ti is equal to 1 otherwise. For the rest, it is easy to show. Yeah, sorry, I forgot. I should probably. And so a lemma is that if you want to know what the number of HK conjugation classes of maximal theta K split tori is equal to our set U modulo the set of 1 comma minus m. So that set U really measures the number of open orbits modulo. If you apply this, so now take, so this is true for any field. So if you take K is QP, P not equal to 2, because it goes through for P is 2, but there's just more cases, and I don't want to deal with that. Then, as before, I write QP modulo QP square is going to be the set of 1 SP, I think I called it epsilon, PSP and PSP. And where SP is the smallest non-square in the finite field, FP. Then the theorem is that the number of HK conjugacy classes of theta K split tori is, first of all, 1 for M is P and SP. One if P is congruent 1 mod 4 and M is SP. Oh, sorry. P and PSP. My fault. 3. It is 2 for P is congruent 3 mod 4 and M is SP. It's 2 for P is 3 mod 4 and M is 1. And 5, it is 4 for P equal 1 mod 4 and M is 1. And similarly, what you get out of this is that the number of double cosets of PK, GK, AK is going to be equal to 2 for M is SP, P or PSP, and it is equal to 6 for M is equal to 1. There's a few things which are surprising from this example. That's why I put all the details on the board. If M is not equal to 1, the fixed point group is anisotropic. Usually, if things are anisotropic, you expect things to be nice and that there is a unique open orbit. No longer the case, because even in this case, this was kind of the surprising one. While the fixed point group is anisotropic, there's 2 open orbits, because there's an open orbit for each theta K split torus. And so even and so that was a surprise. I didn't expect that. I really expected there to be a unique open orbit. I tried to prove actually for a while that if the fixed point group is anisotropic, then we have a unique open orbit, but no way. In the real case, there is no problem. All maximal theta K split tori are conjugate. Not here. But, so. Yeah. So for the rest of the time today, I wanted to talk about orbit closures. I know this is usually getting in a little bit more technical. I know, and what I need to do is go in a level deeper, and that's probably not going to be pleasant. But so I need to get into more structure theory, and yeah, I'll try to do it as gentle as possible. But nothing here is. I lost my notes, and that is going to be. So, what is happening, and I'm mainly going to focus. There is a strong interplay here of the algebraically closed case. A lot of the techniques used are you prove things over the algebraically closed case, and then you get objects which are no longer theta k-split tori or no longer minimal parabolic k-subgroups, and then you try to break those up later in k orbits. That is also true for a lot of the combinatorics underlying the orbit closures. And so I'll describe what you get if you just take all the k's away in the algebraically closed case, and then how you later on break it up into k orbits. And the result is surprisingly similar, but of course you can only do this if you have a topology on your field. So while over the algebraically closed field, all of the results are the same field independent. I'm just going to restrict myself now to local fields because that is where I wanted to give. So I'll assume that we have K a local field. And if I talk about the topology, this will just be the closure in the algebraically closed case. And if I have the T closure, that is then the closure coming from the topology of the field. Yeah? And so it is probably safer that I set that restriction now, but a lot of these things go through for arbitrary fields. But yeah. So I need to talk about what there is a natural map. We have our orbit set Vk, and we can map them into a Well group and a subset of the Well group of what's called the theta. Twisted theta split twisted involutions. So there's a map to Ik contained in the Well group of a maximal in Gk of maximal k-split torus. And let me explain the map to you. I lost my place in my notes, so sorry. Here we go. Wrong section. So my set ik is the set of W in W for which theta of W is W inverse. And this is called the theta twisted involutions in W. There is a natural set, so this map here I'm going to call Vk. The way you get that, if you take an element V in Vk, then there is a representative which I call X of V in script Vk. And then I let my Vk of V is going to be the tau of xv. And that is going to be in the normalizer, we know. But if I want to have it in the well group, I just multiply it with the centralizer and gk of A. Yeah, so that's the coset in the well group. Now, this element satisfies, if you let theta act on this, basically you only need to look what happens at this element. And so this is the set of elements of x, theta, x inverse. If you let theta act on this, it goes to its inverse. So this is a map into these theta twisted involutions. And this map it actually tells you a lot about, there will be something like a Brugha order on the orbit, and the Brugha order is just going to be naturally an orbit is contained in the closure of another orbit, and then that's the usual Brugha order. And that will be described by similar combinatorics on the set of twisted involutions. So in the case, what we need to do, the problem here is that theta doesn't leave. We don't have no longer that theta of p is no longer equal to p. And if you have a theta stable Borel, that means that the basis goes to the basis. Now, if theta p doesn't go to p, then theta doesn't fix a basis. And that is important in the description of this. Yeah, and so that implies that theta of delta is not equal to delta if delta is the basis of phi of A. And so that is a problem we need to address. And so in order to do that, you kind of go to another involution, which is a little bit shifted. And so so note, I'm going to abbreviate. So I'm going to basically say that phi is going to be phi of A, and W is just going to be the well group of A, etc. I'm trying to abbreviate all of that because I'm choosing a set of positive roots, and I want to fix that. So let W0 in W, that is the unique element, such that theta of phi plus is going to be equal to W0 of phi plus. That is basically the correction factor. Yeah? We know from this that this is usually not the case, but there is always a well group element which sends the positive roots back to itself. Then I'm going to take theta prime is theta W0. And I'm going to work now with theta prime rather than with, and if I have a W in I, K, then I'm going to replace that by a W prime, which is a W0. So I'm going to shift everything by W0. So note that W0 is actually a twisted involution itself. We also have that theta prime of V plus is V plus. Yeah, the positive roots go to itself. Theta prime is an involution. And last but not least is that if you have the I corresponding to theta prime, because that is the same as the IK corresponding to theta, and then shifted by W0. So you basically shift your twisted involutions a little bit. So the theorem is that if you have a W in IK, and we have W prime is W0, and I, so this is IK theta, and this is IK theta prime, like I had over here. Then there exists S1 up to SH in sigma, which is the set of the S alpha I, for which the alpha I is in delta. But our V plus had a basis delta. And these are just the simple reflections in the generators. And there exists a sigma prime stable subset pi of delta, such that we can write W prime is S1 up to SH, then H, and then just W pi 0, and then theta prime of S1 up to theta prime of SH. I can put inverses here, but that doesn't matter. Yeah. So this is just this one. W0 of pi is the longest involution of the subset, the root system corresponding to the subset of the basis. Now, so what this is that this is all a twist, and this piece basically represents an involution which flips a part of the theta k split part of the torus to an anisotropic torus, and so that is basically what is something what flips a part of the root system. This is important because this decomposition describes the orbit closure. And so how this part works, this will give you nicely the orbit closure. And that's why I had to explain this.
divided by 0 is equal to the theta prime of all.
Yeah. Yeah, this theta prime becomes an involution, but it doesn't need to be defined over K anymore. But it leaves invariant a parabolic subgroup, which is no longer minimal parabolic K subgroup. So there is lots of messy things behind this. But so then I need to introduce one more small thing. If P is in minimal parabolic K subgroup, we can kind of choose the smallest minimal parabolic K subgroup containing this corresponding to a simple root. And so it is slightly different, of course, than in the algebraically closed version. So let me just write it out. So this contains a maximal K-split torus theta stable. And we have phi of phi is phi of A, same notation. We have phi plus as before. Sigma is the set of S alpha, alpha and delta. We can define for alpha and delta, we define a parabolic subgroup P alpha. And this is the standard parabolic which contains P, and such that the root system of P alpha with respect to A is just going to be, we need to look at all the integer multiples of alpha intersection our root system phi, union all the positive roots. So we just add, but twice a root can be a root in this case, and often less. Most of these root systems are of BC types. So essentially what you have is that the dimension of your P alpha is going to be your dimension of P plus the dimension of all the root spaces G alpha, where no, not alpha, G gamma, where gamma is all the root spaces in Z alpha intersection phi. And this can be quite big sometimes. So I am now ready to describe the orbit closures. So if I have a V in Vk, I have our X is XV in script Vk a representative. Let me write the orbit OV is just Px H. We know that if we apply tau to x, that is going to be contained in the normalizer. So I'm going to, and that is in the normalizer in GK of A. And W is the corresponding Velcro group. So I need a little bit more. So we have that T contained in A is going to be a maximal torus, and we have a basis because that is the root system we are using here, and so we have a set of positive roots, and so I'm going to choose N1 up to N8 in the normalizer in G of T with images S1 up to S8 in sigma. Yeah, so that is, I just need elements corresponding to the simple roots. And to simplify notation, I will write P for alpha I in delta. I will write Pi is P of alpha I because it is much nicer. Otherwise, we get way too many sub-indices. Maybe I should put this up and then. So the theorem is as follows. I'm first going to do the algebraically closed case. So notation as has been set up over here. So the closure of P acting on N. And so that is basically the Vel group element, the element in the normalizer, is just going to be P1, P2, up to P8, corresponding to the simple roots which you find coming out from these simple reflections, acting on the P pi, acting on M. And I should have told you what M was. I'll do I can probably read here. We have here this all these this twisted part of this twisted involution. If you strip this part away first, then you're going to have something left over here. So if I take U is going to be N8 inverse times N1 inverse applied to X, and M is going to be tau of U. And so this describes the orbit closure. If we want to put it, so this is the twisted action. If we just want to have it in the other characterization, where as double coset, so the closure of OV, which is the same as the closure just of the orbit P X8, that is then P1 times P8 times P pi on the orbit of U. And there's lots of dimension formulas. And theorem K local then essentially the T closure of pk, that's going to be bad notation. Let me denote k rational points like that. Acting on our element n is the k rational points of P1 times the k rational points of P8, acting on the T closure of pk. So very similar. And it basically breaks down in analyzing this involution, and you go down in orbits. And something what easily follows from this that pk times hk is closed in gk. So if and only if the dimension of P8 is the minimum dimension of the dimension of all the orbits. So here you look at the dimension of the algebraically closed field, but it still gives you the minimum dimension of the orbits over the p-helix or any other local field. And similarly, the open orbits are exactly the ones which is, there's a unique open orbit corresponding to P8. And so the way that splits up is, again, the same open orbit over any field with the topology. There's lots more you can do here. There is a natural Brugha order corresponding to these orbit closures. We can say that V is going to be less or equal than V prime if and only if the orbit of V is contained in the closure of the orbit of V prime. This is what is the usual Brugha order. There is Springer and Richardson gave a description of the algebraically closed case for that, and that really depends on properties of these twisted type of involutions. Something similar goes through over the p-helix and the reals, but it is more difficult. And the main difficulty here is that there is no longer a unique open orbit. And that makes the combinatorics much more difficult. Okay, I hope that everybody is not asleep, because I know this is usually quite grueling to go through these through all these details. My students fall asleep, so I think everybody else will fall asleep as well. So I'll keep it at this, but I could tell you much more about the representation, but I would need a lot more time than this.